Hey everyone, welcome back to Everything is Relative. I'm Mr. K, and today we're going to be looking at some topical past paper questions, specifically on the topic of nuclear physics. And this is from the Papa Cambridge website for Cambridge A-level physics. Now, I'll leave a link to these questions or to the website where you'll find these questions in the description below. And like always, these questions are a good source of revision if you want to practice topic by topic. So in the last video, I solved some problems from the paper that's labeled Particle and Nuclear Physics, and those questions were primarily on binding energies and fission and fusion and so on. And today's questions will be from 429 as they are numbered to 437, which deal more with radioactive decay. So the first question, and again the numbering I would just rewrite. This is 429. This is the subject code is 9702. This is from summer 2018. So that's May, June 2018. This is question paper 4, variant 2, and question 12 from that paper. And the first question says, state what is meant by radioactive decay. Usually the first questions always ask us to state or define something. So what do we know about radioactive decay? Now, radioactive decay is the random, I like to always have the word random, and spontaneous process. Remember, it's spontaneous meaning it doesn't need any external influence. It'll happen on its own without any extra force or energy, etc. So it's a random and spontaneous, specifically emission of particles, or you can say of radiation, by specifically an unstable nucleus. Remember, a stable nucleus is not going to undergo radioactive decay, but an unstable nucleus will. And so we can say it is the random and spontaneous emission of particles or radiation by an unstable nucleus. And that's a radioactive decay. So very specifically what is meant by radioactive decay, and that's what we've written. Now part B says an unstable nuclide P has a decay constant lambda P and decays to form a nuclide D. This nuclide D is unstable and decays with decay constant lambda D to form a stable nuclide S. So we have a decay chain that is shown in this figure. And we are told that the symbols P, D, and S are not the nuclide symbols. So they just use random letters to represent the different nuclides. Now initially a radioactive sample only contains nuclide P. The variation with time of the number of nuclei of each of the three nuclides in the sample is shown in the graph below. So quite a complicated graph. One of these represents nuclide P, one of them represents nuclide D, and the other one represents nuclide S. And we have to try, I'm guessing we have to try and figure out which one is which. So yes, the first question says, on figure 12.2, use the symbols P, D, and S to identify the curve for each of the three nuclides. Okay, so nuclide P is the one that I initially have. It then decays into D, D then decays into S, and S is a stable nuclide. So initially, I have all my nuclei of P and none of D and S. So the number for P should start from 0. But there's two graphs that start from 0 here. Okay. What I also know is that nuclide S is stable. So the number of S atoms or number of S nuclei will never decrease. It'll constantly increase because it's not undergoing any further decay. It's not splitting up any further. So nuclide S is the one that always increases. Now I can see that this is the graph that always increases. This is the stable thing. It starts at 0. P decays into D, decays into S, and S just continues to grow since it doesn't undergo any decay. So immediately I know that's the graph for S. I also know that I start with a large number of P, but I start with 0 nuclei of D. So the other graph that starts from 0 must be the graph for D. Kind of makes sense though. I have a lot of D initially and then it just decays into S with time. And you can see the relationship between D and S. And lastly, nuclide P, the original nuclide, has a maximum number, the highest number of nuclei to begin with, and then decreases rapidly as it forms D, and then D forms S. So my final graph, or the one starting from the maximum point, will be P. And so now I've labeled the three graphs as I've been asked. So yes, the graph looks complicated, but with a simple bit of inference, you can tell which graph belongs to which nuclide. Remember, radioactive chains mean not only the parent nuclide is radioactive, but so too are the daughter nuclides. And some radioactive chains can be very long. So just be wary that radioactive decay can happen multiple times for a specific sequence. We're then told that the half-life of nuclide P is 60 minutes, and we are asked to find the decay constant lambda P in per second of this nuclide. So how am I going to find the decay constant if I'm given the half-life? Well, luckily, I know an expression to relate the half-life to the decay constant. The half-life is the log of 2, which is 0.693, divided by lambda, the decay constant, which means that the decay constant lambda is the log of 2 divided by the half-life for any substance. And this is the log of 2 divided by the half-life. Now I want it in per second, so I have to convert the time from minutes to seconds. 60 minutes has 3,600 seconds, and so I'll get a value for lambda P to be 1.93 times 10 to the minus 4 per second. So that's the decay constant, the probability of a nucleus decaying every second. And so lambda P, I always like to write my final answer on the dotted line to the correct number of significant figures. In this case, I can use 3. That's 1.93 times 10 to the minus 4. Next, we are shown another decay chain, and we are told that in the decay chain shown in figure 12.1, which is our original figure, lambda P is approximately equal to 5 lambda D. So the decay constant for P is much greater than D, which kind of makes sense because we'd expect P to be more radioactive. And so it would have a high decay constant, meaning its graph has a steeper gradient. It decays much quicker than D does, which we can see from the graph. Now we are given the decay chain of a different nuclide E, where E decays into F and F decays into G. The decay constant of nuclide F, which is lambda F, is very much larger than the decay constant lambda E of nuclide E. By reference to the half-life of nuclide F, explain why the number of nuclei of nuclide F in the sample is always small. Wow, so we have to refer to the half-life of F, which is the nuclide in the middle of this chain, and then explain why it always has a low number of nuclei. Now what we know is from above that the decay constant is proportional, or rather inversely proportional, to the half-life. If you have a long half-life, you have a low decay constant, and vice versa. So what this means is that and they told us specifically that the decay constant of F is much larger than the decay constant of E. So lambda F is much greater than lambda E, and from the expression I've initially written, this means that the half-life of E, I'm just going to use a superscript, is much greater than the half-life of F. So E has a much greater half-life, which means F is more likely to decay more rapidly. So there'll always be more of E than there will be of F. F will decay almost immediately. And so I can write this in words as follows. So I can say E has I don't have to do the mathematics, but I just did for illustration purposes. E has a much greater half-life than F, and so the nuclei of whatever F is will decay almost immediately. If something has a short half-life, it doesn't live very long. It becomes half its mass very quickly, and so those nuclei undergo radioactive decay. And in that process, we don't have to say this, but in that process, G is produced. When F decays, G is produced. So G is being produced quite rapidly, meaning there'll be a lot of G and a lot less of F and a lot of E. And so that's what a low or a high decay constant tells us. There's going to be a low half-life and vice versa. So essentially here you were meant to identify the relationship between the decay constant and the half-life. Now the next question is, again I'll write this down, this is question 430, and this comes from the question paper Summer 2018, question paper 4, variant 3, and this is question 13 in that paper. So the first question says, like before, state what is meant by radioactive decay. And again, being lazy, actually you can't be lazy in an exam, but I can right now, I'm going to copy and paste what I wrote before, because radioactive decay hasn't changed in meaning. It is the random and spontaneous emission of particles or radiation by an unstable nucleus. Remember to include the unstable nucleus part. We are then given a very nice graph which shows the variation with time of the number of technetium-101 nuclei in a sample of radioactive material. So rest assured they're going to ask us to use this graph to find something. And they do. They say use figure 13.1 to determine the activity in becquerel of the sample of technetium-101 at t is equal to 14 minutes and show you're working. So what I know is A is delta n by delta t. So I could find the gradient of the graph at 14 minutes by drawing a tangent, but I don't need to. That would work, but it's not going to be an ideal scenario because drawing a tangent is going to be quite difficult. Rather, what I will do is I will look for 14 minutes on the graph and I will read off the number of nuclei. And it turns out that the number of nuclei here would be 4.4 when t is equal to 14 minutes. And the original number of nuclei, I can write that down now, as you can see, is 8.8. And don't forget, this is times 10 to the power 7. Now, why would I do that? Because instead of using the gradient, I can say that the activity at any point is lambda times the number of particles at that point. And lambda, like we said before, is log 2 over the half-life. So this is n times the natural log of 2 divided by the half-life of technetium. But wait, I don't have the half-life. So what I first need to do is, let me at least find the numerator. Now the numerator is the number of particles at t is equal to 14 minutes, which is 4.4 times 10 to the power 7. Remember, there was 10 to the power 7 in the units for the number of molecules. And we multiply this by the natural log of 2, and we divide it by the half-life. Now, what is the half-life? The half-life is the time it takes for the initial value of n to go to half its value. Well, it turns out that luckily for us, that half of 8.8 is equal to 4.4. No advanced maths required. And so that also happens to be 14 minutes. So this time is also 14 minutes. So we got lucky that the half-life is also 14 minutes. And so this is 14, and we'll convert this to seconds because we want to calculate the activity in becquerel, which is per second. And we get 3.63 times 10 to the power 4 becquerel. And so our activity at 14 minutes is 3.6 times 10 to the power 4 becquerel, to two significant figures. Remember that activity is not constant. It changes as the number of radioactive nuclei change with time. Next, they say, without calculating the half-life of technetium, use your answer in 1 to determine the decay constant of technetium. Well, I've written the equation for A in terms of lambda and in terms of n, so I can rearrange that and say lambda is equal to the activity over n. I'm not calculating the half-life. So without calculating the half-life, I can find lambda, the decay constant. And this is 3.63 0.63 times 10 to the power 4 becquerel as calculated above, and the number of molecules at that point when the activity is 3.64 or 3.63 times 10 to the 4 is 4.4 times 10 to the power 7. And so the decay constant, this is a constant, will be 8.25 times 10 to the minus 4 per second. So the two significant figures, lambda is 8.3 times 10 to the minus 4 per second. And so that's the decay constant for technetium 101. So technetium is also a radioactive isotope. The next question is question 431, and this is from the winter exam, so November-December 2018, question paper 4, variant 1, and this is question 12 from that paper. And believe it or not, we have the same question again. You can see that it's likely that this question will come out in an exam. State what is meant by radioactive decay. So you can probably close your eyes and give me this statement. It is the random and spontaneous emission of particles or radiation by an unstable nucleus. And very similar to the last question, we are given the variation with time of the number of undecayed nuclei in a sample of a radioactive isotope. So this time we don't know what this radioactive isotope is, but we're given the number of radioactive nuclei with time, and time is in hours here. And this question says, use the gradient of the line in the figure to determine the activity in becquerel of the sample at t is equal to 4 hours and show your working. So I now have to use the gradient. I can't rely on the method that I used in the previous question. And what I know about the activity is at any moment in time, it is the gradient of the graph of n against t, delta n by delta t at that specific time. So what I need to do is I need to draw a tangent to the graph, and the tangent to the graph must touch the graph where t is equal to 4 hours. They specifically asked us for the activity when t is equal to 4 hours. So we have drawn my x. I need to now draw a tangent line. I don't know how well this is going to work, but we'll attempt it nonetheless. So I'm going to take my pen. As for you, what you would do is take your pencil and draw a tangent line. And so the tangent line just needs to cut the graph at that point. Again, you have to make sure your pencil is sharp and make sure you're doing this as well as you can. Not poorly like I am, but with a sharp pencil, you should find that that's what your tangent line is. I now need to find the gradient of this tangent line. The gradient of this tangent line is always constant. And what I find is you can use any points along that line as long as it lies on the tangent line. And what I find is that my gradient, I'm going to use is 4.8 minus 0 times 10 to the power 10 on the y-axis. So I'm going to use the y-intercept and the x-intercept, or rather the y-intercept and 0. So the values that I use are going to be very straightforward to read off. And over 10.8 minus 0 on the time axis, and I want to convert this to seconds, so I multiply hours by 3,600 and say 3,600 seconds in an hour. And what I get is an activity of 1.23 times 10 to the power 6 becquerels. I can't be that accurate at the third significant figure, so I can write this activity as 1.2 times 10 to the power 6 becquerels. And so that's how you would use the gradient of the graph if you were to find the activity. Look for the gradient of the graph of n versus t, but you have to find it for the tangent line at that specific time that's given. If I change the time, the tangent line changes gradient, and so the value of the activity changes. So you could also check that your answer very quickly if you had time by doing the method that we did previously. A is equal to lambda n, where lambda is log 2 over the half-life, figure out the half-life, put it into the equation, and see if you can find the activity. And you can see if your answer is more or less correct using that method. We're then told to use your answer in 1 to show that the decay constant lambda of the isotope is approximately 4 times 10 to the minus 5. Same as before, lambda is A over n, because A is lambda n. This is the activity of 1.23 times 10 to the power 6 becquerel divided by the number of nuclei at n is equal to 4 hours. If we do this accurately enough, we'll find that at 4 hours we have 3.05 times 10 to the power 10. And so that's 3.05 times 10 to the power 10. And what we get is a decay constant of 4 times 10 to the minus 5 per second, which is what the question asked of us, to show that we get a decay constant of 4 times 10 to the minus 5 per second. Now the last part of the question says a sample of a different radioactive isotope has an initial activity of 4.6 times 10 to the 3 becquerels, and the sample must be stored until its activity is safe and is reduced to 1 times 10 to the 3 becquerels. The decay constant is 5.5 times 10 to the minus 7 per second, and the products are not radioactive. We want to find the minimum time in days for which the sample must be stored. So we have the initial activity, and we have some activity that's going to be safe, and we want to know how long it will take for the sample to reach the safe activity. And so what we remember, radioactive decay equation, is that the activity at any time t is equal to the initial activity A naught times e to the minus lambda t, where lambda is the decay constant. If I do a little bit of mathemagic, what I get is t is equal to the natural log of A naught over A divided by lambda. So since I remove the minus sign, log of A over A naught has become log of A naught over A. So a little bit of mathematics for you to do step by step there. I've skipped a few steps. And so this is the log of the initial activity, 4.6, divided by the activity that's safe after time t has elapsed, which is 1. I'm ignoring the powers of 3 because they'll cancel anyway. And then I divide this by the decay constant, which thankfully is given in the correct units, 5.5 times 10 to the minus 7. Well, actually, it's given in per second, and we want the answer in days, so we're going to have to convert. And we get an answer of 2.77 times 10 to the power 6 seconds, which is 2.77 million seconds. And then I divide this by the number of seconds in a day. Don't ask questions, but this is 86,400 seconds every day. The curse of being a physics teacher is you never forget numbers like these. 86,400 seconds make one day. And what I get is the sample needs to be stored for 32.1 days, or to two significant figures, 32 days. And so I use the radioactive decay equation to rearrange and solve for time. Make sure you are able to manipulate this equation to solve for lambda or t or anything that you need to. And so you have to be relatively comfortable with natural logs and the natural base e, and the log laws as well. And so it takes 32 days for this sample to now be safe to use. The next question is numbered 433. And this question is from winter 2017. It's question paper 4, variant 1, and this is question 12 from that paper. We're told that a radiation detector is placed close to a radioactive source. The detector does not surround the source, and radiation is emitted in all directions, and as a result, the activity of the source and the measured count rate are different. Suggest two other reasons why the activity and the measured count rate may be different. So they gave us one reason, and that's because radiation is emitted in all directions, And so since the radiation detector doesn't surround the source, if radiation is emitted in all directions, the count rate and the activity are going to be different. You'd expect them to be the same. The per second should be the thing that's picking up on your detector. How many hits per second am I seeing? It's not always the case. And there's a few reasons for this. Now, one of the reasons is that some of the radiation may be absorbed in air. So before it reaches the detector, it is absorbed in the air between the source and the detector itself. If you've ever seen a Geiger counter connected to a detector or to a count meter, you'll know that this count rates are definitely random and definitely difficult to get a steady read on. So it may be absorbed in air before reaching the detector. It's one of the reasons why the count rate wouldn't actually match the activity, the expected activity. And another reason might be the presence of background radiation. So background radiation, just as radiation is random, background radiation will also be random and will strike the detector randomly. And so the presence of background radiation will also change the activity and the count rate. In fact, the count rate will always be different whenever you use the exact same source, because the presence of background radiation will change the values very slightly. And there could be other reasons, such as the daughter nuclei being radioactive as well, so that changing the count rate. There could be radiation that is lost or absorbed by the source itself. So the source absorbs some radiation and doesn't go to the detector. And there are other reasons, and you can look at the mark scheme to see the other reasons. But there are a multitude of reasons why the count rate and the activity will never be the same. At least with your standard Geiger counter and the way we measure it in the lab, there will be many different reasons. So you have a few options of writing, but try only to write 2, because if you write more than 2, you have the possibility, you become more likely of contradicting yourself and not scoring the 2 marks. So just be very wary. Write the 2 that you are most confident in on the answer sheet. We're then told that the variation with time of the measured count rate is shown in figure 12.1. So kind of similar to what we've seen before, but it's more jagged in shape. It's not a smooth curve. This is us using a detector, and we find this jagged shape. And the first question says, state the feature of the figure that indicates the random nature of the radioactive decay. But we just actually mentioned it. This curve is not smooth. Or you can say that the curve is jagged, or the line is not a smooth line. Since the curve is not smooth, I cannot predict exactly when radioactive decay will occur, but I can predict on average that it's going to look like this with time. So you can see for any specific radioactive decay, I can't tell exactly when it's going to happen. But on average, I can tell what it's going to look like with a lot of time. And so that's why we say radioactive decay is a random process. And because the curve is not smooth, we know that this is true. Radioactive decay is random. We're then told to use the figure to determine the half-life of the radioactive isotope in the source. Okay, so then remember, the half-life is the time it takes for the source to drop to half its initial count rate. And I don't have a smooth graph here, so this is going to be a little bit tricky, hence this is 4-mark question. So normally with a smooth curve, maybe 2 marks to calculate the half-life. Now the initial activity, A0, I can go to the graph and I can read it off from the graph, and I get a value which might be slightly different from the value you get, but stick with what you can read from the graph. Your graph might be clearer than the one I've printed. A0 is 172 counts per minute. That's the initial activity. The half-life is the time it takes for this count rate to drop to half that value. So for half A0, if I put this in the calculator, half of 172 is 86 per minute. This means that the half-life is the time it takes for the count rate to reach 86. And so what I do is I use my ruler very carefully. I look for 86. It's going to be somewhere there. Again, I'm not doing this very accurately. And so what I need to do is find the time that corresponds with the cross that I've drawn. And again, I'm doing it quite haphazardly. You would definitely use a ruler and a sharp pencil. And what I find is this half-life is 1.6 hours. Because on the time axis, our time is measured in hours and the count rate per minute. I can't be satisfied that that's my answer though. I can't write half-life equal to 1.6 hours because this graph is showing some randomness. So to be more safe, what I'll do is I'll wait for the count rate to drop by half its value again. So a quarter of the initial value, which is 43 minutes. So the time it takes, 43 per minute rather, the time it takes to go from 86 to 43 is another half-life. And so the quarter life, if there was such a thing, is 3.5 hours. That is the time it takes to get to 43. And again, 43 is somewhere here. Again, very poorly drawn. That's 43 is a half of 86. And the time it takes to get there is 3.5 hours. So that means that the half-life is half of this value. And what I find is 1.75 hours. So what I have now is two values for the half-life. And so I can find an average of these two values to get a more accurate answer. So remember, when I'm uncertain about things, I should take multiple readings of those things. And what I find is 1.68 hours, which again might differ from what you find. But I've said that this half-life is approximately 1.7 hours. So you'd have to look at the graph and try to estimate, and you could even do it again. You could do half of 43, which would be 21 and a half. Find the time it takes to get to that point, and then calculate the half-life again. 2 times for us is enough, but 3 times would be even better, and you could get a half-life to even more accuracy, ensuring that you use your ruler. So because we had to use the graph a few times and do some averaging, this is why this is a 4-mark question rather than a 2 or 3-mark question. For C, we are told the readings in B were obtained at room temperature. A second sample of this isotope is heated to a temperature of 500 degrees Celsius, and the initial count rate at T is equal to 0 is the same as it was in B. The variation with time T of the measured count rate from the heated source is determined, and we want to state with a reason the difference in any, firstly in the half-life. Now, will there be a difference in half-life if I now heat the radioactive substance? Remember what we said about radioactive decay 3 times already in this video. Radioactive decay is spontaneous. Spontaneous means it's not influenced by any external factors. So there will be no change in the half-life. If there was a change in the half-life, radioactive decay would not be a spontaneous process. It would be affected by temperature, proportional to temperature, or inversely proportional to temperature, or something like that. But since the decay is spontaneous, there is no change in the half-life. So there's no difference in the half-life. It stays the same. What about the measured count rate for any specific time? Well, we're going to have a problem. If we look at this graph without any influence at all, I have the jagged line with the count rate. So there's no way that I can tell what the difference would be for the count rate if I change the temperature, because as I can see, the count rate is a random process, and there's other factors that are influencing it as well, such as the background radiation, like we said, such as radiation being absorbed in air and so on. So since the count rate is random, we cannot make any reasonable predictions about what the count rate will be if I heat, and cannot be predicted. I can't make any reasonable predictions about what's going to happen to the count rate when the sample is heated, because the count rate is random to begin with. If it were a much smoother curve, it would be maybe easier to make a prediction, but the count rate is random. And so this question in totality was 10 marks, so quite a significant significantly long question as well. Next we have question 434 as numbered in the Papa Cambridge questions. Again, the subject code is 9702, which is A-level physics. This is from the winter 2017 exam. Question paper 4, variant 2, and this is from question 12 in that paper. We are told that the isotope iodine-131 is radioactive and has a decay constant of 8.6 times 10 to the minus 2 per day. Beta minus particles are emitted with a maximum energy of 0.61 mega electron volts. And first we want to state what is meant by radioactive. Now be very careful, they didn't ask for radioactive decay in this case, they asked for radioactive. So what does radioactive mean? Radioactive means that a nucleus is unstable and will randomly and spontaneously, emit radiation. Unstable nucleus, I should say an unstable nucleus, not an unstable. Unstable what? An unstable nucleus that randomly and spontaneously emits particles, or you can say emits radiation. So radioactive means any unstable nucleus that randomly and spontaneously emits particles. So be careful, this is not asking us to state radioactive decay. And we are then asked to state what is meant by the decay constant. Well, this you already know. The decay constant is the probability per unit time. It's measured in per second. So it's the probability per unit time that a nucleus will undergo radioactive decay. The higher the value, the more radioactive the substance. The lower the value, the less radioactive the substance. The probability per unit time that a nucleus will decay. We are next asked in B to explain why the emitted beta particles have a range of energies. So you're going to have to dig into your knowledge of particle physics from AS physics and explain why the beta particles, the beta minus particles, don't have a single energy. Now usually when we have a reaction like this, if the energies have ranges, it usually means that the energy is shared. So the energy, and you will know this from your studies of beta decay, energy released in beta decay, and beta minus decay also has an emission of a very special particle, which is an antineutrino. So the energy released in beta decay is shared between the beta minus particle and the neutrino. So neutrinos are small, they are very light, but they still get some of the energy. They're still sent off with some kinetic energy. So beta decay, yes, a lot of the energy goes to the beta particle as well. It moves off with 99% the speed of light, but the neutrino also gets some of that energy. And so the beta particles can have a range of energies depending on how much energy is given to the neutrino. So we can never have a single energy beta minus particle coming out from in beta decay. Part C says a sample of blood contains 1.2 times 10 to the minus 9 grams of iodine-131, and we want to find for the sample the activity of iodine-131. Okay, so activity is lambda n. Great. We don't have the number of molecules of iodine-131, but we do have its mass. And we are given the decay constant, thankfully. We are given lambda. So how do I get rid of n? Well, I can write this, if I remember my chemistry, as lambda times the mass over the molar mass of iodine. And this I can figure from the information given. Now lambda is 8.6 times 10 to the minus 2 per day, multiplied by the mass of the sample, which is 1.2 times 10 to the minus 9 grams, or 10 to the minus 12 kg, which is the SI unit. My activity is in becquerel, so all my units have to be in SI. Now the molar mass of iodine-131, it has 131 nucleons. So it's 131 times the atomic mass unit, 1.66 times 10 to the minus 27 in kg. And I have to divide this time, since we had 8.6 times 10 to the minus 2 per day. I have to take this value and divide it by the number of seconds in a day, which again, like I said, is 86,400. So what I get is an activity of 5.49 times 10 to the power 6 becquerel. Or to two significant figures, 5.5 times 10 to the power 6 becquerel. So I could still use my activity equation, but I had to remember that I don't have the number of molecules, but I had to remember some chemistry. Number of molecules is mass over molar mass. Mass is given, molar mass can be determined since I'm told it's iodine 131. I know the number of nucleons it has, and so I know roughly what its molar mass will be. The next part of the question says, determine for the sample of blood the time for the activity to be reduced to 1/50th of its initial activity. So what we need is A over A naught, which we know from the radioactive decay equation is e to the minus lambda t, to be 1 over 50. The final value needs to be 1/50th of the initial value. And so I can do a little bit of mathematics here. I get lambda t is the natural log of 50, get rid of the minus sign, and I flip the fraction. So the time t is the natural log of 50 divided by the decay constant. I can keep the decay constant in days, in per day, because the time I need to measure is in days. So that's 8.6 times 10 to the minus 2, 0.086. And so this time that it'll take for the iodine to reduce to 1/50th of its activity, of its initial activity, is 45.48 days, which to two significant figures is 45 days. So whenever you are told that the activity or the number of radioactive nuclei drops to a certain number of its initial value, you use the radioactive decay equation, and more than likely you're going to have to solve for the time, which means you have to rearrange, manipulate that equation to solve for the time using your natural logs. Now the next question is question 436. This is again 9702. This is from the March 2016 exam. Question paper 4, variant 2, and this is from question 13 in that paper. We are told that beryllium-7 is produced in the upper atmosphere and then sinks down onto the Earth's surface. And nuclei of beryllium-7 decay with a half-life of 53.3 days to form stable nuclei. The activity of a sample of beryllium-7 on a tree leaf is 39 millibecquerels, and we want to show that the decay constant of beryllium-7 is 1.5 times 10 to the minus 7 per second. Well, again, we can do this in our sleep. The half-life is the natural log of 2 over the decay constant, which means that the decay constant is the natural log of 2 divided by the half-life, which I can get from my calculator. The natural log of 2 divided by the half-life is given in days, but we want our decay constant in per second. So it's 53.3 days times 86,400 seconds a day. It's the curse again. And this is 1.5 times 10 to the minus 7 per second as was required. We're then asked to find the mass of beryllium-7 on the leaf. Well, this sounds like it could be a bit tricky, but we actually did something like this in the previous question. The activity is lambda n. I don't know the number of molecules, but I don't want to calculate the number of molecules. I want the mass of the beryllium-7. And so this is lambda times the mass over the molar mass of beryllium-7, which means I can now find how much of beryllium-7 is on the leaf. This is the activity A times the molar mass big M over the decay constant lambda. So if I put in all my values, The activity, I was told, is 39 millibecquerel. 39 times 10 to the minus 3 becquerel times the molar mass, 7 nucleons, times the mass of a nucleon, 1.66 times 10 to the minus 27 kg, divided by the activity, which even if we didn't manage to calculate above, was given to us, 1.5 times 10 to the minus 7 per second. And this gives us the mass of beryllium on the leaf to be 3 times 10 to the power minus 21 kg. So very tiny amount of beryllium-7, 3 times 10 to the minus 21 kg to two significant figures. We are then told that the leaf is covered so that no further beryllium-7 is added to the existing sample from the atmosphere. And we are asked to calculate the time that must elapse before the activity of the sample is reduced to 2 millibecquerel. So again, when we see this, we go immediately to the radioactive decay equation. The current activity over the initial activity is 2 millibecquerel divided by 39 millibecquerel, so simply 2 over 39, which is also equal to e to the minus lambda t, which again, if I solve for t, will be the natural log of 39 divided by 2, all divided by lambda 1.5 times 10 to the minus 7. So how long will it take before the activity reduces to 2 millibecquerel? It's 1.98 times 10 to the 7 seconds. To two significant figures, this is 2 times 10 to the power 7 seconds. And so that question was an interesting one. It's quite a calculation-heavy question, but expect a lot of calculations in this topic, and usually also accompanied by a lot of conceptual understanding. Now the last question for this video is question 437, and this question is from the winter 2016 exam. This is question paper 4, variant 1, and question 12 from that paper. And the first question is a nice change. It says define radioactive half-life. Well, we've said it too many times already, but what is it? It's the time taken for the activity of a radioactive nuclide to be reduced to half its initial activity, or half its initial value, or to drop to half its initial value. Initial or original value. So the time taken for the activity of some radioactive substance to decrease to half its original value. Or you can say the time taken for the number of radioactive nuclei to be reduced to half its original number as well. Either one of those would be acceptable. So that's how we define the half-life. And next we want to show that the half-life is related to the decay constant by lambda t half is 0.693. So we always start with the radioactive decay equation. A is A naught e to the minus lambda t. But the activity drops to half its initial activity after one half-life. So a half of its original value, A naught, is equal to A naught e to the minus lambda, and this time is the half-life, which we call t subscript half. Which means I can now do some math. I get e to the minus lambda times the half-life is equal to a half. So minus lambda times the half-life is equal to the natural log of a half. And I can flip the fraction by removing the minus sign. So I get lambda times the half-life is equal to the natural log of 2 over 1, the natural log of 2. Well, believe it or not, if we put this into the calculator, the natural log of 2 is 0.693. So lambda times the half-life is 0.693, as required. And the last question here says, radon 222 is considered to be an unacceptable health hazard when the activity of radon 222 is greater than 200 becquerels in 1 cubic meter of air. We want to find the minimum mass of radon in 1 cubic meter of air above which the health hazard becomes unacceptable. So I'm going to go back to the method I've done previously, twice before. The activity is lambda n. I know the activity. I don't know the number of molecules that will be acceptable, but I need to find the mass that will be acceptable. And I also know the decay constant. It's given, 2.1 times 10 to the minus 6. So I have to take away n, since I know a and lambda, and I have to replace it with the mass, because I want to find the mass. So again, I can write this as lambda times mass over molar mass, which is number of molecules, which means I can find the acceptable mass, or the minimum mass that is acceptable. And this is the activity A times the molar mass m divided by the decay constant lambda. And this is 200 becquerels, which is the accepted activity, multiplied by the molar mass of radon 222, which is 222 nucleons, times the mass of a nucleon, 1.66 times 10 to the minus 27 kg. That's the atomic mass unit converted to kg, divided by lambda, which is 2.1 times 10 to the minus 6 per second. And I get the acceptable mass to be 3.51 times 10 to the minus 17 kg. Very small mass indeed. Or to two significant figures, 3.5 times 10 to the minus 17 kg. And so you can see we did a lot of questions that looked quite similar. We were rearranging the radioactive decay equation, we were calculating half-life and activity from a graph, and we were learning how to use natural logs and the natural base E. And it was quite mathematical, a lot more mathematical than conceptual. But again, for a topic like nuclear physics, you have to understand both. It's more modern physics, so there's a lot of things that can be asked for you to explain. So I hope this video was helpful. I hope nuclear physics is a bit more easy to understand now. I will continue to keep making videos on these topical past paper problems for different topics in the upcoming days and see how much I can get through. And at some point, a video on paper 5 or a few videos on paper 5 are required as well. But if this video was helpful, please leave a like, leave a comment in the comment section. Let me know if you have any suggestions. Subscribe to the channel. It'll help me out a lot. But for now, that's all from me, Mr. K, on Everything is Relative. I'll see you again next time.